Hello again. Before we talk about tangent planes, I guess I should introduce to you the notion of a partial derivative. So let's write that down. Partial. Let's write that down with my ugly handwriting. Derivative. Wait, am I recording? Hold up. Yeah, I'm recording. Okay, I just had to double check if I was recording or not. Okay. So, what is a partial derivative? Of course, like any other recent video I've done, I'm going to give you the formula first or the notation first, then give you the intuition. So, let's do this in this pretty color. So, this is going to be the notation, and oops, it's going to be a curly d, and a function of of a number of inputs. So I guess you can say x and y, but I'm not gonna write that. And partial of any of its variables. It could be x, it could be y, it could be, I don't know, a, if there is. So let's say it's x for now. So this f right over here with this color. This f right over here is a function of x and y, and let me give you the formal definition and then give you the intuition. So it is the limit as the change of x approaches 0 of the function f of x, damn it, of the function f of x plus change in x, comma, y, minus f of x, y, the quote-unquote original function, or the function with its original inputs, all over change in x. So as you might notice, this looks very similar to the formal definition of a regular derivative in single variable calculus, which is hopefully intuitive to you by now. So like in let me stretch my back first. All right. So like in single variable calculus, we have axes, and we have, let's say, a curve in single variable calculus with this pretty color, and the the derivative of a point, or the instantaneous change about a point, is going to be its tangent line. Ooh, that's pretty. About, let's say, this point. So this at this point is at this point its slope, it's going to be oops it's going to be rise, or in this case I'm drawing it downwards. It's going to be rise over run. Hopefully you know that by now. So what is the intuition behind a partial derivative? Alright, let's draw the x, y, and z axis with a normal color white. Straight line, straight line, straight line, straight line, straight line. Let's label the axes x, y, and z. And let's say we have a plane. I don't know. what kind of plane I'm going to be preparing. Let's say, I don't know, something like this. Let's see. Let's see. Alright, that is the surface. That's going to be the surface. Oh no. That's going to be the surface. Let's say the surface g of xy. So what is a partial derivative? Let's pretend that we can slice the graph in a certain direction we want. Let's say we want to slice the graph parallel to an axis with an axis, let's say parallel to the x-axis. Alright, so let me get my colors, this color. So let me slice this part. Oh no, this is going to be parallel to the y-axis. See, they are parallel. I guess you you could use a visualization tool. So what what do I get from cutting a surface? Cutting part of a surface with a plane. What you get is to see the slope on the CY plane. So if we kind of zoom in, the slope may look something like this. Let's draw it in a similar color. May look something like this. This is the y and the z axis. Alright. So what is a partial derivative? So the partial derivative is going to be the derivative. In this case, it's going to be the derivative of the function g, or let's say z for simplification, over dy, which is, let's say at this point, you have tangent line, this tangent line. Ooh, that looks beautiful. So why do we need an extra notation for partial derivatives is if its idea or principle is almost similar to a derivative? Well, a simple answer to that is, how are you going to differentiate between dz dy and dz dy and dz dx being separate, potentially separate functions? Let's say z is a function of x and also so happens to be or or function of y or a function of x and y. So what is the derivative of this with respect to its inputs? Let's do it with regular notation. So a normal d dz dx, that is the derivative of this one. This one, it's with respect to its inputs, there's only one input. And this one, since there are two inputs, we have dz dx. I'm doing this on purpose. And dz dy. Now, how are you going to differentiate if you were to give me one of these derivatives? How am I going to differentiate between a multivariable function or a single variable function? So that's where the what do you call that? The partial derivative notation comes in handy, and that's from the last video. Alright, so the partial derivative is useful to distinguish between a single variable derivative and a multivariable derivative, or in this case a partial. There's oh well, better not explain things where I'm out of line. Alright, partial z, partial y. Now you can clearly see the difference between a single variable function and a single variable and a multivariable function. And to give you more intuition, I guess, let's draw the line. Let's draw somewhere here. Alright, so let's do one example on how to calculate a partial derivative. How you calculate it is, as you can see in this visual graph, you set whenever you take the partial derivative of a variable, let's say in this case of an input, that's what I meant, you have to set the other input constant so you can get the slope or the derivative about at a point y or x, but in this case y. So the value of x here is color yellow, is this. Let's say this is c, or I don't know, b, or v, or any constant c. Let's say c. So let's do an example. What is, so we have a function called f of xy instead, f of xy. F of xy so happens to be, let's say x squared, x squared, that doesn't look like a 2, x squared plus y squared, and we want to know what is the partial derivative. Let's switch to new colors. New colors. You want to know what is the partial, nope, what is the partial derivative of the function f with respect to x, and what's the partial derivative of the function with respect to y. So let's get our beautiful colors, and let's choose this. So what is the partial derivative of f with respect to x? So as I said, whenever you take the partial derivative of something, it's like taking a slice, and that slice is the slice of the plane that's going to be slicing the graph is going to be parallel to the axis that you're going to take the partial derivative of the functions. Never thought of the wording, but I guess you know what I mean. So it's basically this figure, but in words. It's going to be this figure in words. This figure in words. So we want to set y constant and set x as the variable. So y, let's say x squared. Oh no. And we're back. And we're back. Alright. So let's do this first. So we want to make y constant, or pretend that y is a constant. So let's say y is c. So that means that, so that's for visual purposes, and I'm going to erase it for now. So that means it's going to be 2x plus the derivative of a constant is 0. So that's going to be 0. So I don't need to write 0. And for the partial derivative of the function with respect to y, it's going to be in this, I don't know, in this plain color. It's going to be the constant 0 plus 2y. I don't have to write the constant 0. I don't have to write 0, so we have 2y. And we're done.